Hello, fluorescent fans. Recently had the pleasure of working with this flashlight reviewer, FWOD, and he did a fantastic review of my full-wave light. Caveat though, I did sponsor the video, but he had full rights to do whatever he wants. I didn't want any editorial control, and as you can see from the email, I just let him do whatever he wanted with it, even a destructive teardown if he wanted to. Let's see what he said, and I'll give you guys additional information in case he missed it during the review.
The FWOD combines three carefully selected.
Okay, so this is the first thing that I wanted to talk about, because when working with UV LEDs, I was wondering what these were at first, and there's probably one right here, I think, just not shown in this shot. But these are Zener diodes, and they actually help prevent things like reverse voltage. They give you a little bit of protection against static electricity, and these things have been super solid. None of my customers' lights have had any issues. I also wanted to talk about the LED on the left and the right here. So these are both photon wave LEDs, but this one is the one that's special because it's the latest one. There's not even any mention of it online anywhere outside of my product. So I'm super happy about that. And the way you can tell is that it has these little circles right here in their chip mask. Whereas this one, the older version, had longer lines. And this one is about 30% more efficient. But also, you can see this silver thing around it. Why would that be? Let's take a look at the next shot.
The ISO standard categorizes ultraviolet light into three groups, which includes long wave or...
Okay, so if we take a look at the shot here, we've got the two photon wave LEDs. This bottom one here is the newer one, whereas the one on top is the older design. So you remember the thing that I was pointing out? It's actually a reflector. And I believe, I'm still learning about this, by the way, so take this with a grain of salt, but I believe that it's two different types of light extraction. So the top one, I believe, is transverse electric, and the bottom one is transverse magnetic. And so, first of all, what does that even mean? So, with UV LEDs, in particular UVB, UVC, there's not really an established meta. So, with white light LEDs and even UVA LEDs, they're all transverse electric. Let's pretend we had the LED here. So, it will emit light outwards. And that's pretty much to be expected. We expect like the LEDs to shine through here, whereas transverse magnetic, it'll actually light up parallel to the LED. So almost like side emitting. And that's why they had these reflectors on here. And you can see that this center portion here is about the same brightness as the sides here. So that's why I think it might be transverse magnetic light extraction. And this is the first UV LED that I've seen do that, but will we see future lights like that? Who knows?
By combining all three bands, long wave, mid wave.
Note that the purple that you're seeing in this shot and in any subsequent shots is a camera artifact, and it's not coming from the light itself.
Safety is important with this light as it emits high energy waves of the type normally blocked by the Earth's ozone.
These are good safety tips. If you're new to the hobby, you should definitely look at this section of the video and take precautions when enjoying this hobby.
Our UVC light plants this into the category of kids array.
Oh, and here's a closer look of that photon wave LED. You can really see the little tiny dot chip mask pattern, and yeah, it's interesting how it has the same intensity of light. The center and the sides, about the same.
The ramp. And I wish the light would stop and clearly blink at the end of the ramp instead of immediately reversing direction.
That is a super valid criticism, and that's actually how it works with more enthusiast flashlights. That's what they'd come to expect. I decided to be more on the cautious side because this was more geared towards rockhounds, though.
When in use, the buttons will only glow for a few seconds before turning off. The three buttons are...
Okay, so the reason the buttons turn off, first of all, is to preserve your night vision. Let me go to the section where it showed the lights on. So It's an interesting crossroads between the flashlight enthusiast and then the rockhound. Because on one hand, I wanted to make it super bright so that you could see it during the daytime if you're at a show and then you want to use the light and you can see which one's on. But on the other hand, it should also turn off so that way you can preserve your night vision.
The medium and shortwave channel run for just a few minutes longer, despite being
Okay, so here's the runtime graphs. Unfortunately, there wasn't anything on when all three are on, so I believe it should be somewhere around here. You'll be getting a little bit over an hour and a half of runtime with all three at max. You wouldn't really want that in the field, just because the long wave would overpower the medium and short. Okay, so let's talk about the actual outputs now. So even though these two end right around the 5 hour mark, FWOD was saying that the long wave is much, much more powerful than the medium and short wave down here. And that's just a function of the newer technology that are these UVB, UVC LEDs. Also, they're much, much more inefficient. So with the long waves, you'll get maybe like 30-ish percent. Let's just put that. So around 30%. Oops. So yeah, around 30% efficiency. And with the medium and shorts, in the best case scenario, you'll be getting around 3%.
rails at a pretty impressive distance. It's not the most powerful UV light I've used, but it's more than enough for honestly anything I could think to use it for. It's a very capable light.
And that's a valid criticism. So the whole light was built pretty much around the latest 255 nanometer LED that I could find. The choice of the 310 nanometer, that was because I wanted to match it with the 255. And it doesn't really make much sense to pick like a super powerful 365 nanometer. So that's why I made the choice to pick the 365 nanometer that I used. It's also a firmware issue where I'm not quite sure how you would do ramping. So if we were to imagine the two output powers relative to one another, let's say these were the 255, 310, and 365. Okay, so here's some arbitrary representations. And FWOD was saying he was already having some difficulty reaching the levels where all three of these would be roughly equal. So if we can imagine I use like the most powerful 365 nanometer and like it goes off the screen, it's so much more powerful. I imagine that it would be even harder to get to this lower level. So that's why everything was balanced around the 255 nanometer LED. I'm guessing there might be a more elegant way to do it in firmware, but that's the reason why I chose the 365 nanometer LED that I did.
The emitters are situated on top of a thick copper MCPCB for better heat dissipation.
Yes, you definitely want a super thick MCPCB for this, just because with the 3% efficiency these had, if you remember, approximately 3%. So the rest of that 97% gets turned to heat, and you've got two of those super big heat producers. So definitely want to do that if you're designing your own light.
Transmission. Much better than other filter types used in flashlights, but they do come at a higher cost.
It's actually a little bit hard to see from this video, but the Dichroics, they're also called thin film coatings. They've got a coating that, in this case, it's golden color. I'll put a picture of what I mean, but they look very different from ZWB glass.
This light is designed to take a 32650 battery, which matches the driver and
Okay, so I definitely want to talk about this. So here is my own label, and you can see it's 5,837 milliamps. That's what I tested it at. It is written 8,200, and that was the pattern that I got when I tested all the other ones. Even the best one that I got, it was like advertised 7,500. I tested it, it was like 6,500. And that's just like a terrible way to start a customer manufacturer relationship. And yeah, that's why I didn't really go with 32650s.
Also included are 3D printed tubes for adapting different battery widths.
So for the 3D printed adapters, I thought this would be the easiest part. I pretty much did it in the home stretch because I thought that all of these were standardized, 18650, 18 millimeters diameter, 65 millimeters long. But it turns out a lot of cell manufacturers don't really follow it super closely. So it was a surprising amount of iteration for just essentially tubes.
I wish there was a way to jump to either extreme, perhaps with a quick double tap, and I wish there was a standard blank to indicate when you've reached the end of the ramp before it begins to reverse direction.
So this was a super interesting conversation that I had with other people that were familiar with enthusiast flashlights, and we couldn't come up with an elegant way to do this. So you can't really do double clicks because sometimes you want to test for phosphorescence, and that looks like this. So if you'll notice, we press it on and then off really quick just to see the phosphorescence. And that wouldn't really work because in this proposed theory, that would like immediately turn it to the max brightness. So I don't know. This is something that I haven't figured out yet. And definitely as the light gets into more people's hand, maybe we can all come to a consensus on how to do these modes. But for now, it's just like a mystery to me. For sure, double clicking wouldn't work. But yeah, I'm open to suggestions.
Levels. Because the emitters each possess their own reflector well, the hotspots of the beams don't perfectly overlap each other, which is especially noticeable, really only noticeable at close range. This is something to note if you're using the light for mineral display.
Yep, that's true. I don't think you would normally be that close to a specimen. You have to be within a couple inches in order for that to happen. Once you get 6 inches, a foot away, then the beams will come together.
Though obvious, it's still worth noting that this device doesn't really produce light in the visible spectrum, so it's still necessary to carry along a standard flashlight.
So this is actually something that I'm looking into. There are these devices called scintillators that the medical community uses to convert UV light into visible light. And I found a Japanese company that produces lenses for this. And right now I'm just looking for a more affordable option because these are a little bit expensive. The idea is that you would put it on top of your light. So after you're done collecting for the night or when you need to move, you would put it on and that way you could convert the UV wavelengths into something visible.
Device that is very effective for its intended use case. I found it to be actually quite intuitive and quite easy to use, and it did help me actually find real minerals in.
Ooh, that's actually a nice find. Let's see what we've got here. It looks like this green part might be chalcedony, and then you've got like a white coating on top. That could be either caliche or maybe a coating of aragonite or something. I bet if you took it and used the long wave on it, it would be phosphorescent. And for those of you that don't know, phosphorescent means just turn your UV light on and off, and it'll have a glow in the dark type effect. So I hope you've enjoyed the thought process behind what went into this light. And yeah, if you have any questions, leave them down below.